Okay, so we're going to start this next section, which I'm really excited about because it's very, very energetic. It's enlightening. Today we're going to talk about 28.2, and we're going to talk about solar activity. What are your objectives? What are you going to learn? By the time you get done, you're going to say, I can explain how sunspots are related to powerful magnetic fields on the sun. You're going to be able to explain that. We're going to talk about the different things that happen as a result of sunspots. The next thing you're going to do is compare prominence and solar flares. You're going to say, I can compare prominence and solar flares. And then lastly, you're going to be able to describe how the solar wind causes auroras on the Earth. Very exciting. Some of the most beautiful things that I've ever seen, and so I get pretty jacked about this stuff. So the first thing that we talk about is solar activity in the sense of sunspots. Sunspots are on the outside of the sun, or in other words, on the photosphere of the sun, and it's being caused by magnetic fields. Well, how does it work? By the way, let me explain this. Cooler, when I talk about cooler, that's kind of a relative term, right? So cooler is when the sun is 6,000 degrees Celsius. Cooler is 4,500 degrees Celsius, 3,000 degrees Celsius, right? So it's slightly cooler in the sense that it is colder, but it's still hot. So as we look at this, we talk about the fact that magnetic fields on the sun are slowing down the convective currents, and as a result of that, the energy is not being transferred. And so if it's not being transferred, then it's cooler. And because that's exactly how it happens. Now, we talked earlier about this. Bright white light on a star means it's like 30,000 degrees Celsius, right? Versus bright or dark light on a star. So if we say reds and oranges, somewhere in the 5,000 to 6,000 degrees Celsius range. So it makes sense that the darker spots on the sun are they dark? No, they're just they're a deeper shade of the color, right? So now here's the interesting thing. I love this statement. Large sunspots are more than 100,000 kilometers in diameter. The Earth, where we are at right now, is 40,000 kilometers in diameter. The sunspots are larger than the Earth, almost by a factor of 3. That is what's so cool, right? And so we're thinking about these massive areas. Observing the sunspots, obviously we learn about the sun. We learn about what's going on about the processes that are taking place in the sun. We are learning so much from what happens on the sun because we're able to see the sunspots and then measure the changes. Now, we have to have a special telescope to look at these things, right? And so to look at the sunspots, we have to have a solar telescope. And solar telescopes, what are they doing? They are blocking or filtering out the light and such that we're able to look at it, because you can't stare at the sun, you can't look at the sun. This is a good image. You can see granulation in this picture on the sun's surface, but then you see this large, massive area of a sunspot, and this is a huge sunspot. Now, interestingly enough, this cycle of electromagnetic energy on the sun follows a 11-year path, an 11-year cycle, and that cycle is such that it's its highest peak in the 11th year, and it's at its lowest peak in the beginning of the cycle. So it ramps up and ramps down, ramps up and ramps down. So halfway through an 11-year cycle, it's at the lowest point. At the top of the point, it's at its highest point. And we see a lot of things associated with that as a result of that 11-year cycle. So this would be an example here of a small sunspot activity, but a large sunspot. That sunspot that you see right there is larger than the Earth, but there isn't a lot there. Okay, a prominence and a flare. There is a difference between prominences and flares, right? So when we think about a prominence, I think of an arch of solar gas leaping from the sun, streaming away from the sun in the solar winds, trying to get away from the sun. But then the magnetic forces and the gravity of that sun pulling it back. And as it's doing that gravity pulling it back to the surface of the sun, creating this giant arch. And what's cool about these things is these giant arches, we've seen them last in upwards of over a year. An entire year that they've been there, which is cray. I've got a really cool picture I want to show you here in about 2 seconds that kind of puts things into perspective. A solar flare, these are the ones that got away. In other words, there was so much energy released from the sun that it went out into outer space. And it goes out in a 360 degree, it's in a sphere, so it's going out in any direction. Ironically, it can go away from us, but more importantly, or worse, it can go towards us. And so you see them travel anywhere from 1,000 meters, 1,000 kilometers per minute away from the sun. And what does that mean? That means it's traveling extremely fast. And so we'll see from the ejection, we call them coronal mass ejections, CMEs, coronal mass ejections. I'll talk about that in a minute, but it can take about an hour for it to come from the sun to us. We talked about the fact that light travels in 8.3 minutes to us. Again, where do the solar flares come from? They're coming from locations near these sunspots, and they're just massively, massively going out in outer space. What's interesting is just depends on how violent that storm is or how violent it can be. But again, peak times, we see these flares, 5 to 10 of them, all at one time, and they go out. We refer to these as magnetic storms, right? Basically a giant disturbance of the Earth's magnetic field. Why? Because what happens when that solar flare hits us, it can totally disrupt everything that's going on the planet. I mean everything. So for example, back in the 1970s, we had a huge coronal mass ejection, and when it did, it struck the planet and overloaded our power grid to the point that the eastern side of the United States lost power and all went into blackout because it overloaded. If we go back in the 1800s, we saw another monstrous CME take place, wiped out the entire telegraph system, right? All gone. Well, imagine if that happens today, and what happens? We rely on satellites, we rely on so much instruments that it could totally cause a massive, massive disruption of everything on our planet. So this is a huge, huge solar prominence, and I put this link on here because I think it's a pretty cool article on solar flares and what goes on with solar flares. It's a great video or a great link to that. And so I'll play this here real quick. Just a second. So this is a huge solar flare erupting.
presented by Science at NASA. Years ago, in 2008 and 2009, an eerie quiet descended on the Sun. Sunspot counts dropped to historically low levels, and solar flares ceased altogether. As the longest and deepest solar minimum in a century unfolded, bored solar physicists wondered when solar max would ever return. They can stop wondering. It's back, says Dean Pesnell of the Goddard Space Flight Center. Solar max has arrived. Pesnell is a leading member of the NOAA-NASA Solar Prediction Panel, a blue-ribbon group of solar physicists who meet from time to time to forecast future solar cycles. It's not as easy as it sounds. Although textbooks call it the 11-year solar cycle, the actual cycle can take anywhere from 9 to 14 years to complete. Some solar maxes are strong, others weak, and sometimes, as happened for nearly 70 years in the 17th century, the solar cycle can vanish altogether. Pesnell points to a number of factors that signal solar max conditions in 2014. The Sun's magnetic field has flipped. We are starting to see the development of long coronal holes, and oh yes, sunspot counts are cresting. Another panelist, Doug Biesecker of the NOAA Space Weather Prediction Center, agrees with Pesnell. Solar maximum is here, finally. According to an analysis Biesecker presented at NOAA's Space Weather Workshop in April, the sunspot number for solar cycle 24 is near its peak right now. They agree on another point too. It is not very impressive. This solar cycle continues to rank among the weakest on record, comments Ron Turner of Analytics Services Incorporated, who serves as a senior science advisor to NASA's Innovative Advanced Concepts program. To illustrate the point, he plotted the smoothed sunspot number of cycle 24 versus the previous 23 cycles since 1755. In the historical record, there are only a few solar maxima weaker than this one. As a result, many researchers have started calling the ongoing peak a mini-max. Pesnell believes that solar cycle 24, such as it is, will probably start fading by 2015. Ironically, that is when some of the bigger flares and magnetic storms could occur.
Huge flare.
Biesecker has analyzed historical records of solar activity, and he finds that most large events, such as strong flares and significant geomagnetic storms, typically occur in the declining phase of solar cycles, even weak ones. Indeed, this mini-max has already unleashed one of the strongest storms in recorded history. On July 23, 2012, a plasma cloud, or CME, rocketed away from the Sun as fast as 3,000 kilometers per second, more than 4 times faster than a typical eruption. The storm tore through Earth orbit, but fortunately Earth wasn't there. Instead, it hit NASA's Stereo A spacecraft, which recorded the event for analysis. Researchers now believe the eruption was as significant as the iconic Carrington event of 1859, a solar storm that set telegraph offices on fire and sparked northern lights as far south as Hawaii. If the 2012 superstorm had hit Earth, the damage to power grids and satellites would have been significant. It all adds up to one thing. We're not out of the woods yet, says Pesnell. Even a mini-max can stir up major space weather, and there's more to come as the cycles. For more news about the Sun and other stars, stay tuned to science.nasa.gov.
So, excellent examples of CMEs and basically I was very impressed with the footage, and that footage came from the Stereo Observatory. Here's another one. This one's already time-lapsed in, but what I think is pretty interesting is if you look, the surface of the Sun, it's coming back, being pulled back by the gravity. But you look up in the right-hand corner of this, right? So we see granulation, we see the sunspots being much brighter or darker around there. But look at the size of the Earth. The Earth could actually fit inside this arch without any problem. Maybe 5 or 6 of them, and so even more. So pretty good image here. I wanted to put this in here, and I think it's a good example of that solar prominence right there, and again the energy coming from that. Here is a big CME, coronal mass ejection. This is this piece up here on the left-hand side. Again, the Sun in this picture, they used a solar telescope which actually blots out the Sun, and the Sun is basically blotted out from the sky, which is not a reference to a Rolling Stones article, Rolling Stone song. Anyhow, this is something I thought was pretty interesting. I actually copied this. This was in 2003. We had a CME in 2003. What I find extremely interesting is if you look in the red areas, it says associated with the flare was an injection of 1 billion tons or more of gas from the sun's tenuous outer atmosphere of the corona. All right, these guys are talking exactly what we're talking about in a newspaper, and then it goes on. It takes roughly 8 minutes to travel from the sun to Earth. These particles are made the trip in less than an hour. Here's what really stands out to me. This was in the Pontiac Daily Leader. I took this from the Pontiac Daily Leader in 2003, and what they said was there was going to be a huge, huge solar storm hit. Our own local paper picks up on the issue. Here's a massive, massive solar storm leaving the sun. Down here below, you can see the sunspots associated with that, and again, that energy leaving the sun from around the sunspots, the solar flares leaving the sun. Again, CMEs, most powerful explosions in the solar system, right? So this is the rest of the paper. They're caused by magnetic lines. They get tangled and they snap back into position, right? So what it's talking about is the fact that the sun switches its magnetic field. This is a good example. This is the solar energy, the magnetic storm leaving the sun. This one is kind of cool. So what do we get when we just have normal solar winds strike the Earth? They're called auroras, right? Aurora Borealis in the northern hemisphere, Aurora Australis in the southern hemisphere. So the magnetic storm hits the Earth's ionosphere and it charges the air. It electrically charges the particles by the magnetic poles. And so basically as they strike, they produce these sheets of electrified particles that are yellow and green and red and blue. And most of the time we see them in the north and south poles, which is interesting. Once you've seen them, 2003, that's when I saw them here in Pontiac, Illinois. That was that same storm, right? I was in Sonneman, actually, and that same storm hits. As it does, the auroras are here in Pontiac. And what did we see? We saw blues and reds and oranges and yellows up in the nighttime sky. Very quickly, once you see it one time, you will then understand why the ancestors of our planet, the people who live in areas that see a lot of the auroras, it's easy to understand why they connected the auroras, with their ancestors in the heavens, people who had passed away, because it's such a moving experience to see, and it was easy to understand how they can connect this to the heavens above, right? So again, what I'd like to do is show you a couple really good examples of the auroras. I think you'll find it pretty interesting. This first one, they're both from National Geographic. This first one, really good example of what auroras look like. So this is a group of people who are out having a good time. You'll note that they get a bonfire going over here, right? I'm not sure what they're putting on the bonfire, but it's hauling major booty there. But notice the auroras in the background, this ribbon of light. And if you look at this, again, this is time-lapsed, but it's like a river of electricity lighting up the nighttime sky. These guys pretty quick, they pose for a picture here. They're like, man, this is cool. Let's pose for a picture. It's easy to understand how people could get excited about this. It's so gorgeous. I think they just put another log on the fire. Look at this ribbon. And again, this ribbon is streaming over a period of minutes. And most often we see greens. Every once in a while we'll see the deep blues and reds. Somebody just put another log on the fire. Missing the ribbons above. All right. This next one, this is from Norway. I thought it was pretty cool. This one is just different settings in Norway, and it doesn't always have to be in the winter time, but winter we see an increase in them. It happens all year. Look at the pronunciation of these colors. Oh my gosh. So gorgeous. I love how when they play these videos like this, they always have this massively powerful music that goes along with it. And again, these are time-lapsed. So it keeps on going, but that is so cool. I think that's good stuff, right? So I could probably sit and watch that the entire time. All right, so to finish up here again, we have seen the auroras now. I want to point out that, what were our goals today? Our goals were to be able to explain how sunspots are related to powerful magnetic storms of the sun, compare solar prominences and solar flares. We saw all of that. And then describe how a solar wind can cause the auroras on the Earth. And a lot of research being done on auroras, but real cool stuff. So I want to say thanks for paying attention and listening, and I hope you have a great day.